previous video, we started talking about external flow, and by previous video, what I mean is that I've color coded it for you. So the videos that are that have got a thumbnail in gray, we're talking about fluid mechanics in those videos. So the last video I did was an introduction on external flow. I'm going to be continuing on with that because now we need to basically look at external flow past different kinds of objects. Like there can be complex objects like airplanes, let's say, or it can be any less complex object, like you could say a sphere or a cylinder. So we need to be dealing with external flows past objects. And that is a wide range of fluid phenomena. And you could think about cars moving on the streets, air flowing over them. That's external flow past a car. That is an object. You could think about an airplane. Again, air moving across the plane or right in front of it. So that's again external flow past the airplane, past an object. So just like that, these are two examples that you visually see. And then there's so much more. You walking, just the act of you walking, that is external flow past your body, past an object. So before we move on to looking at the complex objects in the way of the flow, we need to look at more simpler objects. It could be a sphere, it could be a cylinder. So, and then we need to look at the characteristics of this external flow. By that, what I mean is that what is the flow going to be like? What could be the velocity of the flow when it's flowing across the object? And then that depends, and very strongly depends on a lot of different parameters. Could be the size of the object that against which the flow is moving past. It could be how the object is placed in front of the flow. That means you're looking at the orientation of the object. It could be the speed of the flow. That means you're looking at the velocity profile of the flow. Or it could be the fluid properties itself. Are you looking at flow, let's say, flow like airflow, or are you looking at flow like water? Or maybe you are more interested in experimenting with different other things. It could be, let's say, different kinds of oils. So you need to be looking at external flow when it comes to that. So then, like I've already talked about viscous flow, and I've talked about pipe flow as well. So when it came to pipe flow, we were looking at dimensional analysis approach, and that is the one that we're going to be applying here as well, because that then makes our analysis a lot simpler in a lot of cases. And when we talk about the dimensional analysis approach, there's three different dimensionless products that are very important. So the first one is definitely the Reynolds number, because Reynolds number is going to, and this is typically the most important parameter when it comes to external flow. So Reynolds number is going to indicate the most important parameter, the most important dimensionless number. Then you've got the Mach number, right? And then if you're looking at flows with a free surface, and what that means is that you're looking at, let's say, a ship, and that is moving in two different flows at the same time. So you've got an interface between the two fluids now. And then when you're dealing with interfaces, you're also looking at Froude number. Okay, so just go ahead and look at these definitions again. It's also important for you to understand what the characteristic length is when we're talking about these dimensionless numbers. So make sure you go ahead and review what these are. Reynolds number is obviously representing the ratio of the inertial to viscous forces. And when there's an absence of viscous forces, because what is Reynolds number? It's basically rho, which is density, into velocity, into your characteristic length, divided by viscosity, which is represented by mu. So Reynolds number is representing the ratio of the inertial effects to the viscous effects. And in the absence of viscous effects, what that means is that this is going to be equal to 0. In the absence of viscous effects, this Reynolds number then becomes infinite, right? Because it's 0. And on the other hand, if there's an absence of all inertial effects, then this entire thing becomes 0, right? Because then that means that either you've got negligible mass or then the density is 0. So the Reynolds number then becomes 0 in that case. But clearly, when we talk about an actual flow, a Reynolds number is going to be between these two extremities. And what that means is that there's not going to be an absence of viscous force, and there's not going to be an absence of inertial effects as well. So any actual flow will have a Reynolds number between 0 and infinity, right? So then the nature of the flow past any body is going to depend strongly on whether Reynolds number is really, really small, right? Or Reynolds number is much, much larger, right? So then in that case, obviously, you could say that you're approaching negligible inertial effects or negligible viscous effects. But with most external flows, and this you will see quite often, the fluids that are involved that we're dealing with are typically either water or air. And then the resulting Reynolds number range for flows like that is approximately, well, Reynolds number for these kind of flows is between, on the higher end, it's less than 10 to the power 9. And on the lower end, it's greater than 10. Okay. And as a rule of thumb, what we say is that flows that have a Reynolds number of greater than 100 are dominated by inertial effects. So just remember that. If Reynolds number is greater than 100, what you say is that the flow is being dominated by inertial effects. And if the Reynolds number is less than 1, then the flow is being dominated by the viscous effects. Okay? But in actuality, most external flows that we look at in real-life applications are dominated by inertia. So that means inertial effects. And that means that flows have Reynolds number greater than 100. But at the same time, you've got external flows in which, real-life external flows in which Reynolds number is considerably less than 1. And that means a lot lower than 1. And that can be, the example can be, for example, you've got a particle, a small dust particle that is settling into a lake. Now that is that's going to have a very low Reynolds number. Okay, and then obviously things change when we go down to that scale of Reynolds number. Or it could be that Reynolds number for, let's say, objects that are moving in really high viscosity oils. So then for that as well, because mu is really high, and that means that Reynolds number becomes really low. So we're gonna look at, in this video, two things. We're gonna look at flows past two different kinds of objects. We're gonna be looking at a flat plate. So a flat plate is probably the simplest kind of object across which we can look at the fluid. So we can basically have a fluid which is flowing towards this plate, and how basically this flow is going to change depending on what the Reynolds number is when it interacts with this plate. So that is what we're going to look at. And the other thing that we're going to look at is a circular cylinder, and how the flow is going to be interacting with that circular cylinder depending on how you change the Reynolds number, depending on whether you increase or decrease this Reynolds number. So first we're going to look at flow past this plate, flat plate. And to do that, well, we're going to move on to a case where Reynolds number is really small, right? So because the Reynolds number is small, only 0.1, what that means is that the viscous effects are going to be relatively strong, and the plate is going to be affecting not just the flow, because, okay, so two terminologies important. Flow that is to the left side, because flow is flowing from this side, this is the upstream side, and then this is the downstream, right? So when the flow is such that the Reynolds number is really small, 0.1, that means that the viscous effects are stronger, and the plate, this plate, affects this uniform upstream flow in a way such that it's not only affecting it in the downstream direction, but it's also affecting it above the plate, below the plate, and behind the plate as well. Okay, so this entire area, it's being affected because of the fact that the Reynolds number is so small. So then the viscous effects start dominating, right? And what that means is that in low Reynolds number flows, the viscous effects are not only felt close to the object, but they're also felt far away from the object in all directions. Okay, so that is just one thing to see. You've got a uniform flow upstream of this plate, and what you see is that when this flow interacts with the stream, with the plate, you've got an imaginary, this is an imaginary boundary that we've created here. And we create this boundary based on the fact that once, let's say, this flow goes ahead, let me get this. Once this flow goes ahead and interacts with this plate, obviously the fluid is going to be displaced, right? And that means there's going to be a change in the velocity as well. So you've got velocity over here, which you're indicating by capital U. And then once you start moving over here, the velocity has decreased now. Okay. Even the flow that is closer here, that's going to have a decreased velocity too, because you've got fluid coming from here that is displacing the particles over here. And that means that the velocity is going to be changing. So because of this, because the layer next to the layer, next to the layer, next to the layer, you've got a situation where the viscous effects are impacting the velocity profile. And now at the end, or some place far away from this plate, you're going to have velocity that is not going to have any effect at all. The velocity is going to be the same here. It's going to be capital U. And that is what you see here, that this imaginary boundary that is being created here, we're going to talk about it in the next video as well, but just to give you a hint, this imaginary boundary is called the boundary layer. And boundary layer is defined such that the velocity is basically 99% of the maximum velocity, and the maximum velocity is capital U. So you've got maximum velocity here, and then obviously when you look at the profile of the velocity, it's going to be the smallest at the plate, because just like when we talked about pipe flow, we said that at the pipe walls the velocity is going to be 0. So that is what is being indicated here. And then the velocity is going to be increasing once you go away from the plate or go away from the pipe wall. That is exactly what is happening here. And then the velocity is going to keep on increasing, in this case for the flat plate, until you reach the maximum velocity that is already the velocity of the flow. Okay, so this boundary layer, then you've got to find a point where you can basically say that, okay, this is as far away from the plate where the viscous effects hold any real significance. Of course, this does not mean that the viscosity is 0 or something over here. The viscosity is the same. That much is understood. But the effect of the viscous flow, or the effect of viscosity, is not felt um, that far away from the flow. Okay, so what I'm trying to say is the velocity is 0 here, and then obviously it's increasing until the point that, let's say over here, the velocity has reached. So if, let's say, capital U over here is 100 meters per second, just as an example. Okay, I'm just going to simplify it for you. There's going to be a point where the velocity is going to be 99 meters per second, right? Well, basically, that is the point where we say that the boundary layer, that's the end of the boundary layer, okay? And that is what is being indicated by this over here. Yeah, so this is the case when Reynolds number is really low. Moving on to the next case, and that means that as we start increasing the Reynolds number, and how are we going to do that? The simplest way to do it is if we increase the velocity. So then the Reynolds number has increased, and the region in which the viscous effects are important start becoming smaller in all directions, upwards, downwards, behind the plate, except for the downstream one. Okay, so you don't need to travel very far away from the flow now to find a point where the velocity is basically going to be as low as, like if we consider the previous case, the velocity is going to become higher at a much faster rate, and that means, just to put it in simple words like that, and that means that the boundary layer is going to be smaller as well. Okay. Just like that, if we keep on increasing the Reynolds number, and now we've got these two cases, I'm going to show you the next case. We increase the Reynolds number even more, a lot more, and what we find is then that the boundary layer becomes even smaller, and the boundary layer is just the region of thickness, basically. It's a thin region on the surface of a body anyway, but it's the region in which the viscous effects are important, and outside of this, fluid essentially behaves as if it's inviscid, but obviously that does not mean that the actual viscosity of the fluid is changing or something. The viscosity is the same whether it's within the boundary layer or outside the boundary layer. It's just that the relative importance of the viscous effects, and that is because the velocity gradients that I just previously explained, is different within and outside of the boundary layer. And the boundary layer is a very, very important concept. It was proposed by Ludwig Prandtl, who is a big name in aerodynamics. He was a German physicist as well, and he conceived this idea of the boundary layer. And because of this idea, which we're going to look at in the next video, and the equations that he came up with, the assumptions that you could make, using this hypothesis of boundary layer, it was possible for him, and then his student as well, I'm not going to name him right now, in the next video again, it was possible for them to simplify the analysis of large Reynolds number flow, and then basically they were able to find out solution to external flow problems that couldn't be solved otherwise. Okay, so this Reynolds number, when it's way, way higher, the flow is obviously then being dominated by the inertial effects. And that is why the viscous effects are going to be negligible everywhere except in the region that is very close to the plate. And the main reason for that is that you've got the no-slip boundary condition. We've talked about this as well before when we were looking at pipe flow. We talked about the no-slip boundary condition. And what that meant was that the fluid is going to stick to the surface. The fluid layer that is right next to the surface is going to stick to the solid surface. And that means that the velocity is going to be 0. So then obviously if the velocity is 0 here, you cannot have a jump in a way that if velocity is 0 here, it's going to be, just taking the same example, it's going to come up to 100 meters per second straight away in the next fluid layer, right? So it needs some time to develop. And that means you're going to have some kind of velocity profile here, and then you're going to have a constant velocity once you've achieved that maximum velocity possible, which is capital U. Okay, so that is the third case. Another thing that I should just mention here is basically this symbol over here, which is delta. This indicates the thickness of the boundary layer. And the thickness of the boundary layer is relative to the length of the plate is really, really small. Okay, so this is, right now we're talking about, in a way, we've talked about these three cases, and we're talking about a streamlined flow because we're letting the flow develop, but then there are bodies which are not streamlined, right? So then obviously we need to look at those bodies as well and how the flow is going to be past those bodies. And those bodies are called blunt objects. And one of the examples for it is the circular cylinder. So then we have to look at that circular cylinder and how the flow varies across that circular cylinder based on, let's say, the changing Reynolds number. And again, in general, as the Reynolds number is increasing, the region of flow in which viscous effects are important are going to be is going to be becoming smaller, just like we've seen right now. But for blunt bodies, or bodies that are not sufficiently streamlined, another characteristic that we observe is flow separation. And flow separation is that you will see basically once you've got, let's say, this cylinder over here, ignore my drawing, and once flow starts flowing past this cylinder at higher Reynolds numbers, you've got basically regions developing here where you're going to see that flow starts separating. Okay, so that is one major difference between the streamlined bodies and blunt body objects. So with lower Reynolds number, again, we're looking at 0.1 past the cylinder. Viscous effects are being felt, obviously, throughout in a relatively larger flow field. Okay, so the viscous effects, if you look at it in this way, they're important in several diameters. So you could place another cylinder here, you could place another cylinder here, you could place two cylinders here of the same size, a couple of these on top as well. So basically what I'm trying to say is that the flow field that is being affected by the viscous effects is really large in any direction from the cylinder. Okay. Another important aspect is that the streamline pattern that we see is essentially symmetric. So you could basically flip it and mirror it on the other side as well. It's going to look exactly the same. But once you start increasing the Reynolds number, then you lose this symmetry. And what happens is that the viscous effects area in which the viscous effect is important starts becoming smaller. Viscous effects obviously then start convecting downstream of the flow, and well, the separation starts taking place. So you've got flow separating from the body at the separation location, which is, let's say here, it could be any point on this cylinder, and these are called separation locations. So this flow starts separating from the body at the separation location, and the fluid inertia then becomes important, and at some location in the body, obviously, like I've said, you got a separation flow, and then this fluid has so much inertia that it cannot follow this body, this curve, and the fluid can't curve back on top of it. So then that means that the flow is going to go something like this in this direction. And because of that, because the flow cannot follow the curve path around to the rear end of the body, this results in a separation bubble over here behind the cylinder. Okay, so in this, some of the fluid is flowing upstream against the direction of the flow. Okay, so this is one major difference between a streamlined body flow and a blunt body flow. Okay, and then obviously you can start increasing the Reynolds number even further. So from a Reynolds number of 50, you've gone up to 10 to the power 5, and then at even larger Reynolds number, the area that is going to be affected by the viscous forces is again going to be forced downstream. Okay, and then you've got a very thin boundary layer over here. Okay, compared to the diameter on the front portion of the cylinder, and you've got then maybe an irregular, unsteady, maybe turbulent wake region. This is called wake because it's after after passing the body. So then you've got this wake region that then extends downstream of the cylinder. One important thing to remember is that whether or not viscous effects are important, whether viscosity is important, of course viscosity is the same. When I say, again, I'm going to emphasize this point, when I say that viscous effects are important within the boundary layer and they're not important outside of the boundary layer, it does not mean that viscosity becomes zero outside the boundary layer. Okay. But the velocity gradients are much larger in the boundary layer, and we talked about this when we were looking at the flat plate. And then the boundary layer and the wake regions are then a lot larger in the flow field over here. Okay. So what that means is that obviously when viscous effects are important, that means that the shear stress is important as well. And then the viscous effects are basically confined to the boundary layer and the wake regions. So this is what this video was about, characteristics of flow past different kinds of objects, and we classify those objects into two: streamlined objects and blunt body objects. And for both of these kinds of objects, the nature of the flow is going to depend very strongly on the Reynolds number. And usually with most familiar flows, you're going to see that they're going to have larger Reynolds number. Okay. In the next video, we're going to be talking about the boundary layer characteristics. But yeah, just go ahead and look at different examples, try to come up with different scenarios. Maybe go to Munson's book and look at example 9.2. I'm going to also leave the reference for this book in the video caption, so go through that example as well. That will clarify a few questions that you may have related to this video.